For coming for my talk. Today we will talk about Java memory model. As you probably know, it's part of Java language specification, and it describes how thread interacts with memory. So we are mostly familiar with synchronized keyword, how mutual exclusion works, but we often forget that we also have to care about data visibility and data races. All right. Few words about me. I'm a senior software engineer. I work for Ocado Technology in UK in software simulation algorithm development team. And we are one of the teams responsible for our new warehouses where we are writing a control system for thousands of bots which are moving on a grid and helping to pick grocery. So as you can understand, the concurrency is quite important to us. So what we are going to talk about today is we will start with out-of-order execution. We will try to understand why multiple threads, when they're writing, it doesn't mean that some other thread, if it's reading, will have up-to-date information. Then we will have a short introduction to JC Stress framework, which is one of the frameworks from OpenJDK, and it allows you to test assumptions from Java memory model. Next, we will move to concepts and definition from JMM, and we will try to use some examples and puzzles to test our knowledge. All right, so let's start with out-of-order execution. So there are two reasons. Well, in general, there's one reason, which is optimization, but we can divide them on optimizations on the compiler level and optimizations on the hardware level. From perspective of Java memory model, both optimizations are treated the same. However, it's good to understand what's really happening behind the scene. So let's start with compiler optimization. So we know that if you have a Java code, it will be compiled to bytecode using JavaC, and then it will be run on JVM, right? And JVM will profile your application, and as soon as it detects that it's hot enough, a specific method is executed a specific number of times, it will start to optimize. We have two compilers, C1 and C2, and before Java 1.8, you had to select one or the other one, or it will be selected based on the hardware specification. With Java 1.8, we have something called tire compilation, so JVM will decide when to use C1, when to use C2. So what kind of optimizations we can have? Of course, we can have inlining, which is probably the most important one. So instead of calling your method, the content of the method, if it's short enough, will be copied to the place of execution to reduce the amount of jumping to the other locations in the code. What else can we have? Well, if you have short loops, something which is called loop unrolling, so the content of the loop is copied multiple times, so we don't have to create the looping in assembler. If you are calling, for example, a method which is synchronized from a loop, then compiler can detect that, put the synchronize around the loop, and then execute the method directly, because entering and exiting synchronized block is quite expensive. If you have synchronize and monitor, which is just local to the thread, then compiler also can detect that and remove that synchronization completely. And there are many, many other. But what does it mean for our code? Well, let's start with the typical textbook example of multi-thread execution, right? So we have one thread which will start starting, and it will read one flag enabled. And it's intentionally not properly synchronized, because it's just static flag, right? So the one thread is reading in a loop, and the second thread, our main thread, will wait 1 second, and then it will try to terminate by changing the flag to false. So what's supposed to happen? Well, program should terminate. But in reality, what will happen is that the JIT optimization will disable that code completely, because after 1 second, JVM will be warm enough, JIT will optimize it to something like this. So it will read the flag once, put it in some variable, and then refer to that variable in a loop. So in general, whatever you do with the previous variable, it doesn't matter. It will never terminate. How do I know that? Well, you can add extra parameters to JVM. It will print you nice debug options with JIT compiled assembler, and then you can use something like a JIT watch to have nice tree view of your Java code, bytecode, and assembler, and that's poor interpretation of the assembler code. But probably it would be better if we just try that, right? Let's try to run it. So that's exactly the same class, right? And if we execute it, we have start, we have shutdown, but the program is still running because our second thread has not been terminated. And I can run it as many times I want. Nothing will happen. How do I know that it's compile optimization? Well, this is due to inlining, so this part will be inline, and inlining is quite specific, and you can disable it using -xx:\inline. So I can run it with that specific flag. Oh, sorry. Let's run it again. Oh no, that's not what I want to do. Okay, run. So when we run it with that flag enabled, it means inlining is disabled for entire application. And our program is properly terminated. So we fix the problem. However, the entire application is extremely slow because we have just disabled the most important optimization at compiler level. So probably there's a better way of doing that, right? All right. Let's go back to our hardware. So we already know that compiler can reorder our code, but that's not all. We have quite complex hardware these days. And usually when you think about it, it's like, okay, I have a CPU, it has some cores inside, there is memory, and I will have one thread which is running on core 0, second thread on core 5, and they will access the memory directly. One will write, second will read. So no reordering possible, right? The problem here is that our modern CPUs, they're like 3 gigahertz with 3 gigahertz clock. They can execute around more than one microoperation per cycle clock, which means per 1 nanosecond. Accessing memory, on average, is like 60 to 100 nanoseconds, depending on your architecture. Of course, that's like average numbers. So during that time, the processor will waste a lot of resources. So we have to optimize it in some way, right? What can we do? Well, if we zoom in inside that high-level overview, we will notice that there are a number of caches. So there will be like L3 cache in that specific architecture, which is shared between cores, and we have L1 and L2 caches, which are specific to the core. And the access time to L1 cache is like 1 nanosecond, L3 dozens of nanoseconds. But what is also interesting is that our execution engine is a multi-pipeline execution, and it can execute multiple micro-operations in the same time. So we also have something which is called load and store buffers. What are those? Well, so we can execute load and store in the same time. Unfortunately, stores are more expensive, so you have to cache it. And if you think of what are stores? Well, when you write something to memory, so when you're executing x equal 168, that's storing, right? You're putting some value into memory. When you want to use the memory, so if you want to reuse some variable, that's loading because you have to get the value from y and then multiply it by something or add it to something, etc. So what will happen if we want to execute that code? And we want to think about it from perspective of our core 5. Well, the CPU will execute store. It will put the result to our store buffer because it takes a little bit time before you can finish it. So before it's committed and shared between the cores. And in the meantime, we are quite lucky because the results for Y are already inside L1 cache, which means that we will not have cache miss and we don't have to refer to main memory again. So load will be quite fast. Oh, sorry, okay, so we've executed store partially, then we move to load, which is executed, and then finally, the store is committed, is committed to L1 cache, and there is coherence protocols which are exchanging the information between L1 caches. And finally, C1, C5 can see the results. And in the meantime, the coherence protocol will also put the value somewhere into memory. So as you can see, the store and load has been reordered from perspective of C5. And that's not the only reordering which is possible, of course. If we create a table, on one side we have reorderings, on the other side we have different architectures, then you can find out that we can distinguish between two memory models, hardware memory models. The weak memory model, where enough different reorganizations are possible, and then strong memory model, where just stores and loads are possible. So x86 architecture, this is what I have here, is i5 x86, can only reorder stored with loads. But if we go to ARMv7 or alpha, number of different reorderings are possible. And inside that table, which is also interesting, there are assembler instructions, sorry for those, which are memory barriers or memory fences. So those instructions are used to prevent those specific reorderings. So if you have a Java code and you will put volatile somewhere, on x86, it will be executed as some kind of mfence locked or ins, or some other assembly instructions on different architectures. All right, and that's probably a good time to introduce our JC Stress framework. There are two frameworks from OpenJDK, which I use. One is JMH. So if you have to create a benchmark, always use JMH. It will properly warm up your JVM. It will run your code multiple times, give you nice statistics. It will save a lot of time. And if you want to understand the assumptions from Java memory model, then you can use JC Stress. It's still in experimental phase. However, it's already used in a number of tests, a number of new features for Java, like var, handles, etc. So there are a number of tests already included in OpenJDK. So if you want to learn something about Java memory model, it's a good reference point. Both frameworks are quite easy. They are annotation-based. So if you want to create your test, and if you want to have multiple tests in one class, unfortunately they are class-based, so you have to use static classes, and you have to annotate your class with at JC stress test, and at state, and then you can have multiple at outcomes. So at outcomes are your assertions. So right now here I'm assuming that the results from that test will be 1, and is acceptable and interesting. It can be acceptable, forbidden, or unknown. And you can add some description. Inside the test, on your methods, you can put two different annotations. One is at actor, and you can have multiple at actors. Those are entry points for your threads. And you can have one method annotated with at arbiter, and this is executed after all threads has finished to get some results. You can also get results from your at actor by passing a class which is annotated with at results, and there are a number of classes already predefined in JC Stress. So II underscore results, that's two integer results. There's also a different type of operation which is called termination, and in that point, it's more relevant to our first example where we had one infinite loop and then changing the flag which should terminate that loop. So that's why it's called termination. So you have one thread, and then you have to set signal, which is a method annotated with that signal, which should terminate that thread. And if it's not terminated, then framework should kill everything on the end. All right, let's start with first test. So this is the only reordering possible on hardware on x86 architecture, which is store with load. So what we are doing here, we are creating a race condition between writing to x, and then reading the x on the other thread, and writing to y from other thread, and reading it from the first thread. What kind of results can we get? Well, if actor 1 is executed as first, y is still not populated, so we will have 0 in R1. Then actor 2 is executed, x was already populated, so R2 will be 1, so 0, 1 is fine. If actor 2 is executed in the first, then we have 1, 0. If both are executed almost in the same time, then we have 1, 1. What's not possible from that code, without any extra reordering, is to get 0, 0. Because if you have 0 on one side, the second variable was already populated. But we already know that there are store buffers, and they are allowing to reorder the code on the hardware level. And of course, you should write that code in assembler, so Intel specification will provide you how to do it. But we can have similar result running it from Java. Let's try to do it. All right. Let me select our stall load. So as you can see, you can have different number of outcomes, and you can say what kind of results we want to have. And that's exactly the code. Oh, I should probably also describe you how the framework works. Well, it will instantiate your class as many times as possible during 1 second, which is default. And it will execute those threads, get the statistics. It will do it 4 times, and then provide you a summary with all the results. So let's run it. Let's see. And from time to time, because I'm running it from IntelliJ, you have to rebuild the project. So in general, you should run it from command line, just java-jar, blah, blah, blah. And when you run it from IntelliJ, from time to time, it just forgets that it was already compiled. Cool, let's run it again. And now we get some numbers. So as you can see, 0, 0 is quite popular, right? Let's go back to the full results. So we have 0, 0 has the most occurrences, because that's one of the quite important optimization on a hardware level. How do we know that it's a hardware, not a compiler? Well, we can disable compiling, but we can do also something more interesting. We can run both threads on the same CPU. If you're running on the same CPU, in general, it's quite unlikely that they will hit the case when both are executing at the same time. So one is put back to our scheduler, we switch context and then execute the second one. That's possible. But also, even if it happens, then the store buffers have forwarding mechanism, which means that if you're running on the same CPU, you have access to store buffers, even if they are not committed yet. So reordering is simply not possible. So let's try to do it. So how do we do it? You have to go somewhere in Task Manager on Windows, unfortunately. So if you put affinity on your IntelliJ, all other subprocess will inherit that affinity. So let's run it on CPU 1. Now, of course, everything will be slow. So the framework will detect that there's only one core available. We will get less occurrences because, as you can see, however, 0, 0 is not possible. We also don't have 1, 1. Why? Well, because the code is quite small, right? So to have 1, 1, you have to run it almost in the same time or switch the context during execution. So we will have to do something like, oh, come on. So you can do, like, if you want. Whoops. Oh, yes, thread, of course. Thread yield, which means that I don't want to execute that thread anymore. Put it back to scheduler queue as scheduler and do whatever you want next. So if we run it now, we should have some 1, 1, but 0, 0 is still not possible. And so we can understand that, we'll run in a second, the results are based on statistics. So when you don't get errors, doesn't mean that it doesn't exist. Sometimes it's you haven't run it for long enough, or you haven't run it with specific configuration. So you can see 1, 1 is there. And 0, 0 is still not there, so no reordering if you're running on single CPU, but probably we want to run on more CPUs than just one. Let me revert that setting, because right now everything will be extremely slow. Okay, and let's go back to our slides. So we know that we can have reordering on a compiler level. We can have some reorderings on a hardware level. What can we do about them? Well, we need some kind of contract between Java developer, your JVM, and your hardware. And this contract is simply Java memory model. So it describes which writes are visible when you're reading something. And we are quite lucky enough that Java has one of the first memory models for modern languages. And as you can guess, the first memory model in Java was quite broken. So is anyone using Java 1.4? Good. Because if you are using, okay, if you are using Java 1.4 with in concurrent environment, then you can have some problems because you couldn't have thread-safe immutable objects, and you could also reorganize between volatile and non-volatile fields. And what are those thread-safe immutable objects? So imagine that you have a string. String is immutable, right? And in one thread, you are creating the string and creating substring from that string. And then you are sharing the reference to that substring with other threads without any extra synchronization. And because it's not thread-safe in Java 1.4, then the entire content on other thread can be visible as full string or as substring, because you are sharing the backing char array, and all has changed are just the reference point. So that's quite horrible. And reordering between non-volatile and volatile fields, I will go back to that point later on. But with Java 1.5 and JSR 133, everything was fixed. We have nice concurrency package and more powerful volatiles and thread-safe immutable objects, which is quite cool. All right, so what is all about? We have to create some kind of order in our execution. So Java memory model will define number of actions, which are like writing to volatile variable, reading volatile variable, or just writing to variable, reading variable, a number of those. And you have to run those actions on two different threads or multiple threads. And they have to create some kind of relations. And those are the most important ones. So whenever you are exiting your synchronized block and then entering the synchronized block on the other thread, that's one of the synchronized with relations. If you're writing to volatile and reading the volatile, the same volatile, it's another one. Starting a thread, and then first action in the thread, one more. And the final one, when you finish your thread, and when the other thread has detected that the first one has finished, that will be also synchronized with relation. But why do we want to have them? Well, because we can create an order, and that will be called happens before order. So if you want to think about it in single thread execution, it's quite simple, right? It's just like how we're running our code. If action 1 was before action 2, then it happens before action 2. In multi-thread environment, you have to search for your synchronized with relations. So let's think about it here. What kind of ordering we will have, or which writes will be visible from the perspective of thread B. So thread A has operation 1, 2, write to volatile X. That will create a synchronized with relation with reading the volatile X. The write to volatile Z from thread B doesn't have any relation because we are not reading from Z. And then you have synchronized Y, synchronized V, different monitors, no synchronized with relation, and some other operations. So from perspective of thread B, we will have something like this. If we are lucky enough and thread A has been executed first, before, we will have operation 1, write to volatile Z, operation 2, read volatile X, and in that point, the X will be up to date with the latest write from thread A, but we also have access to all other operations which have not been volatile and synchronized, so we have access to operation 1 and 2, to the results of those operations. And then operation 3, synchronized V, operation 4. We don't know anything about operation 3, 4, and 5. The results of those operations can be visible, but we cannot say that they are. All right, let's go to something else. So happens before is one thing, but we also have thread-safe immutable objects. And this is a little bit different. It's not part of happens before order. You have to put final on every field in your class, and then there is a freeze action inside after the constructor has finished. So you can do whatever you want inside the constructor, For example, you can create a hash map, just normal hash map, populate it with data, put it on your final field, and then you can share that entire reference to that object without any extra synchronization. However, if you don't have final, then you are on your own. You have to do whatever you need to provide extra synchronization. So everything is final, freeze action on end of constructor, everything is fine. So one more test. So right now we are creating a static reference to our object because we can share it between threads. However, we have no finals on our x, y, z. Inside constructor, we are adding 1, 2, 3. And one thread, one actor, is creating the object. The second thread is trying to read the values from x, y, z. So if everything is fine, we shouldn't have any zeros. If we have some zeros, then it means that, something is broken, right? So let's try to execute that. Okay. Oops. Okay, that's the right one. So outcome will be 1, 2, 3. Any other outcomes are forbidden. And if we run it, let's see. If there are any zeros, it means that it's not thread safe. And once again, I have to rebuild it. That's annoying. And run it again. All right, let's see. One, two, three, 1, 2, 3. No zeros. Well, but you have to remember that that's x86 architecture. Only reordering from the hardware level is store with loads. All we have right now are just store, because we're just assigning value to some variables. And it seems that compiler is also not optimizing anything around that. So we are fine? Well, not really. What will happen if you run the same code on different architecture? Do you remember our slide where we had a number of different architectures and weak memory model and strong memory model? If you're running on something like, for example, ARMv7, which I have right here, which is Raspberry Pi. So as you can see, it's four cores, and they are ARMv7, which means that they have a weak memory model and a number of different reordering are possible. And if I run the same code, so I have a helper here, am I mutable? So how do you execute the code from command line? With JC stress, so you have to compile it to jar, and then provide -t with your regex, name of the test, -v to have verbose output, because in general it will also create some kind of HTML with some results. And we are also providing JVM args empty, because if you don't provide that argument, it will create more runs with different types of arguments, just to test more. But we want to have a little bit less tests. Let's run it here. And yeah, we have some zeros. So imagine that this code is now running in your production, and yeah, what's happening? How can we fix that? Quite simple, right? All you have to do is to put final on our XYZ. So that's the only change here. And there's no sense to run it on x86 because we already know that it's fine. However, we can run it on Raspberry Pi. So another helper with finally mutable this time, finally mutable, and problem should be solved. You shouldn't have any zeros. So what's the lessons from here? Well, you should remember that you should code against specification, not the implementation. If your specification is telling you, put the final and wait for the freeze action on end of constructor, just do it. If your code is running on your laptop or on your tower, and then you put it on production and it doesn't run because you haven't applied the specification, that's your fault. All right, let's go back to our slides. Okay, how about this one? It's called escape, and the name can tell you something. What we are creating here, it's a volatile static reference to int_supplier, Java 8 functional interface, which will give you an int. And our class is properly constructed. There is a final x. And inside the constructor, we are creating our supplier, and we're also populating x. So once again, the same construct. One thread is trying to create the instance. Second thread is getting the instance and getting the results from supplier and getting it directly from getX. If there are any zeros, it means that something is wrong. All right, let's run it. Escape again. So 1, is acceptable. Everything else is forbidden. And if we execute that one, let's see. Yeah, no, there are zeros. And the 0, if you look at the results, 0 is sitting on R1, because this is R1, this is R2, and our R1 is supplier get X. What's happening here? So you have to remember that constructors are not ordinary methods. They have this freeze action on the end of constructor. And if you allow to escape this during construction, then unfortunately, that's your fault again. So what's happening here, we are creating int_supplier, and it works something like an inner class, so it has access to this before it's fully constructed, and we are putting it on a static reference. Even if it's volatile, it doesn't matter, because our constructor has not finished yet. So remember, don't create threads inside your constructor, don't put this inside to the new threads, or don't expose this on static references before they are fully constructed. All right. But what will happen if, for example, we want to use reflection, right? Because you can modify your final with reflection. Well, Java memory model will tell you that, yeah, you can do it. However, you will have another freeze action after the modification is completed, but I will strongly advise not to do it, because in the meantime, compiler can optimize your code, put those finals directly somewhere, and you will have the visibility of the class in one thread as modified, and in the second one, not modified. So don't do it. And let's go back now to the next topic, the volatiles. So we are now quite clever. We know that volatile will create happens before order, right? So whenever you write to volatile, and then you read from volatile from the second thread, all other operations, even if they are not synchronized, should be properly visible to our second thread. So we can be clever, and we can create a very interesting optimization. And of course, that's not optimization, please believe me. So we are removing one volatile from the code. So what do we have here? So we have mi-synchronized class, and there is y and x. Y is not volatile, x is volatile. And we want to just use the x, and then use our knowledge that writing to y will be visible, because we are using the x as synchronization point. So what is happening in actor 1? Well, we are writing 2 and 3 to y and x, and the actor 2, all it has to do is to multiply those values. It's quite simple, right? So, what kind of results can we get? If actor 2 is executed as first, then we will have 1, because 1 multiplied by 1 is 1. If actor 1 is executed as first, then we will have 6, right? Because 2 multiplied by 3 should be 6. If both are executed almost in the same time, then y will be populated, for example. X is still not populated, so we can have 2. So 1, 6, and 2 are fine. What's not fine is to get number 3. Because if we have number 3, it means that, all right, y has been already populated. Now we have populated x, and then when we are multiplying, we have access only to x, and y is still with initial value 1. So 3 is really bad. All right, let's try to run it. Okay. Once again. Am I synchronized? So we have number of outcomes right now. 1, 2, and 6 are acceptable. 3 is forbidden. Any guesses? What will be the result? All right. And no. So as you can see, there are some number 3s there. So that what implies that our optimization is horrible and doesn't work. Let me show you that again. So we have 3 here with 90,000 occurrences. So what's wrong with our code? Okay, let's go back here. So let's repeat that again. So we have to create a happens before order, which means that we have to write to volatile and then read the same volatile from second thread, and everything after that will be properly visible. Any suggestions how to fix that and what's wrong with that code? Sorry? Yes, that's a very good point. So what's happening here, you're referring to actor 2, right? Yeah. So we are writing to y first, then writing to x. So actor 1 is fine. But what actor 2 is doing? Well, instead of reading x first, it's reading y. So it will read y, then it will read x. And after reading x, we have synchronized with relation, but that's already too late because we have already tried to get the value from y. How do we know that it's happening in that order? Well, Java will tell you that it's probably chapter 15 or something, that the order of execution from that point will be from left to right. Y is first, x is second. How do we fix that? Well, just revert the order. Oops. So x multiplied by y, run it again. And problem should be solved. However, as you can see, if you're going down to those low-level elements and trying to be very clever, it's very bad for your code, because if someone doesn't understand what you have done, it will be very easy to break it. So if you can try to use higher-level abstraction, use something else, and usually you will have just a small piece of code in your application where you have to really care about latency and the number of operations you can process. So if you don't have to, don't use volatiles, because they can create really strange behaviors. All right, so we have fixed the problem. Let's go back to our slides. Let's summarize. So please never ignore concurrency issues. They are real, they can affect your production, and it will be extremely difficult to reproduce it. Always try to find some descriptions from framework which you are using. Always search for happens before order. Every mature framework will have something about that if it's using concurrency. Always code against specification, never implementation, right? Because your implementation, specific hardware can change, and suddenly your code doesn't work, and in most of the cases we don't know where our code will run. And if you want to use thread-safe immutable objects, always put final and then wait until the constructor will finish, and then properly there is a freeze action and you will share the reference between all other threads. All right, and that's basically all. So if you have any questions, we have a few more minutes, and I can try to answer them. Any questions? All right, if there are no questions, then enjoy the rest of the conference, and thank you very much for attending my talk.